In this video, we are going to introduce the eigenvalue problem, which is for any n by n matrix A, we want to find the scalars lambda such that AX is equal to lambda x has a non-zero solution. So this is our formula when we're looking for eigenvalues. We want the transformation of A on X to be equal to lambda x. So notice the transformation, what it does to x is only scales it. It does no rotations. Transformations can be considered as combination. The two things transformations can do is rotate or scale. So in this case, for the eigenvalue, we want to know the lambdas and their corresponding vectors that are only scaled by the transformation. So I'll give you formulas or show you how to find the eigenvectors and eigenvalues of a 2 by 2 matrix, and then and we'll do a couple of examples, and then just talk about the significance of eigenvectors. So we'll back up a little bit again. The eigenvalue problem, we're finding the scalars such that AX equals lambda x has non-zero solutions. So the scalar lambda is called an eigenvalue of A, and any non-zero n by 1 vector x that satisfies this equation, the AX equals lambda x, is called an eigenvector associated to lambda. So again, we look at this eigenvector eigenvalue equation, AX equals lambda x. And if we do some algebraic manipulation, we have AX minus lambda x equals the 0 vector. And then I can factor out my x vector, and I have A minus lambda I. And one of our calculations, I'll show you why this lambda I works. And then again, we were looking for x not equal to the 0 vector. We're looking for non-zero solution. So we're looking for when, looking at this equation, we're looking for when A minus lambda I is non-singular. In other words, has non-trivial solution. In this video, we are only going to look at 2 by 2 matrices, and the other videos will work up to n by n. So let's consider a matrix A equals A, B, C, D. And we're going to look at the eigenvector eigenvalue equation, AX equals lambda x. So here I have AX is equal to lambda x. Again, I want to subtract the lambda x from both sides, so I get AX minus lambda x is equal to 0. And for lambda x, I want to substitute lambda times the identity matrix times x. And to show you why I can do that, I have lambda x is equal to lambda times our 2 by 1 vector, x1, x2, which is just equal to lambda x1, lambda x2. And I'm going to compare that to lambda times the identity matrix times our vector x. So here I have lambda and my identity matrix for the 2 by 2 matrices, and then I have my vector x. So if I multiply lambda times my identity, I get lambda 0, 0 lambda times my vector x, which is equal to lambda x1, lambda x2. So you can see that these two are equal. And now I can make my substitution. I have AX minus lambda times the identity matrix times x equals 0. So now I can factor out my x, and I get A minus lambda, B, and then C, and then D minus lambda here equals 0. And this is where I'm going to leave the solution for now, so we can talk about how to solve this part of the equation. For the 2 by 2 matrix, we're going to use this fact here to solve this eigenvector equation. So we stopped at this point where we had A minus lambda, B, C, D minus lambda x equals 0, 0. So for a 2 by 2 matrix, it is singular if and only if the product of the diagonal entries is equal to the product of its off-diagonal entries. We will do an example, but also you might recognize this formula as a determinant formula. And you will see that later when we go to n by n, it is exactly the determinant. So our example is A is equal to 5, negative 2, 6, negative 2, and we want to find its eigenvalues and eigenvectors. So the eigenvector eigenvalue equation is AX is equal to lambda x. Moving over, we have AX minus lambda x equals 0, and then making this equal to lambda I, we can factor out the x. And so now we have 5 minus lambda, and then 2, and then 6, and then 2 minus lambda. So essentially we're doing the minus lambda on the diagonal, times x equals 0. By our note over here, this matrix is singular, in other words, has non-zero solutions for x when the product of the diagonal entries is equal to the product of the non-diagonal, off-diagonal. So we have the diagonal entries is equal to the product of the off-diagonal, which is the same thing as the product of the diagonal minus the off-diagonal equals 0. Solving algebraically, we get lambda equals 2 or lambda equals 1. So for lambda equals 2 now, we can find the eigenvector associated with lambda equals 2 by looking at our equation, a minus lambda I. So here's a minus lambda I. With lambda, we plugged in 2 for lambda. And I have this resulting matrix, 3 minus 2, 6, and minus 4. And from our eigenvector equation, we want to find non-trivial solutions to the homogeneous equation. So we look at the matrix with 0, 0, and we find that our non-zero homogeneous equations is when 3x1 is equal to 2x2. So for example, if I let x2 equals 1, then x2 equals 1, then x1 has to equal to 2/3. And any scalar multiple a times 2/3 1 will be an eigenvector. And again, the eigenvector means that there's an eigenvalue, in this case 2, such that ax is equal to lambda x. And you can verify that. So you can multiply the matrix A here times this x, and you'll see it's equal to 2 times the x. Similarly, you can solve for lambda equals 1. You can find the eigenvectors associated with lambda equals 1. Oh, here I said, and the eigenvectors for lambda equals 1 is of the form 1/2, 1. And again, for any eigenvalue lambda, the eigenvector, if x is a corresponding eigenvector, then so is any scalar multiple of x. Our final note is the significance of eigenvectors. So if you look at this, what this equation is saying is that your transformation A only scales your vector x. There's no rotation. So these are the vectors that are not rotated by transformation. They are only scaled. Those are the eigenvectors. And the eigenvalue is how much they are scaled by. So these vectors give you important information about the structure of the transformation. And another significance is the choice of basis is important when you choose a basis for a space. So earlier we had seen that orthonormal bases are particularly nice because it's easy to calculate the coordinates. Well, here it turns out that basis of eigenvectors is also particularly nice. In particular, if remember from our last chapter, we said once you know what a transformation does to its basis, you can know what the transformation does to any vector. So let me write that down. Here are the 2 facts we are going to use from our video about linear transformations. First, we said that matrix multiplication is a linear transformation, and then second, we said if T is a linear transformation, then we can represent it with a matrix A. So here, if we're talking about the eigenvector eigenvalue problem, we're talking about matrices, we're talking about transformations. And the thing about linear transformations is T of AU plus BV, where A and B are scalars and U and V are vectors, is equal to A times T of U plus B times T of V. And the key in the linear transformations is if you know how T transforms a basis, then you can determine how it transforms any vector in the space. Because once you have this broken down, if U and V are your basis vectors, then all your vectors can be written in terms of U and V. So we'll do this in terms of our eigenvectors. We'll look at this, how once we have a basis of eigenvectors, how it's easy to figure out what the transformation does on any vector. So to illustrate why a basis of eigenvectors is convenient, is let's assume we have eigenvectors v1, v2, v3 of a matrix A, and the matrix A represents a transform T. So the eigenvectors are linearly independent. So this is a theorem that I haven't gone through yet, but I'm just going to give this to you as a fact. Eigenvectors are linearly independent, and since we have 3 eigenvectors, they will form a basis for R3. So that means any vector in R3 can be written as a linear combination of our v1, v2, and v3 eigenvectors. Then if we take the transform of v, that's the transform of our linear combination of v1, v2, and v3, because it's a linear transformation, that's going to be equal to a1 times t of v1, a2 plus a2, t of v2 plus a3, t of v3. But because v1, v2, and v3 are eigenvectors, this is simply going to be t of v1 is simply lambda 1 v1, and t of v2 is lambda 2 v2, and t of v3 is lambda 3 v3. So mostly this example is to give you a sense of why eigenvectors are nice and their significance. There are many other examples as well. But the idea, again, is that the eigenvectors are the vectors that are not rotated. They are only scaled by your transformation, and they give you a lot of information about the structure of the transformation. Now we've covered the main material of the eigenvalue, or the introduction to the eigenvalue problem. So the eigenvalue problem is to find scalars lambda along with their associated vectors, the eigenvectors, such that ax is equal to lambda x. And then here's our eigenvector eigenvalue equation. Ax equals lambda x. We move over the lambda x, so we have ax minus lambda x equals 0. We factor out the x, which means we need to multiply lambda by I, and we kind of saw why this is how we would do this, and we set that it's still equal to 0. So what we want are non-zero solutions to this equation. So in other words, we want to know when is a minus lambda I non-singular. And we have this example here. We started on a 2 by 2 matrix, and then we have this note that this matrix here is singular if and only if the product of the diagonal is equal to the product of the off diagonal. So we got this equation here, which if you recognize determinants, if you've done determinants, this is exactly the determinant. So to find the eigenvector and eigenvalues of a matrix, you do the a minus lambda I here, and you get this equation, and then you get this algebraic equation, and you can solve for lambda. Once you have lambda, you plug in lambda into a minus lambda I, and you look where this matrix is non-singular. So you solve the homogeneous equation, and you find solutions for x. And then we talked about the significance of eigenvectors. They are the vectors that are not rotated. They are only scaled by the transformation. And this gives you a lot of structure, information about the structure of the transformation. And one example of why this is important is a basis of eigenvectors is particularly nice. For review, I have 2 matrices for you to find this matrice's eigenvectors and eigenvalues, and also the eigenvalues and eigenvectors of the second matrix. And also just verify this calculation. Once you find the eigenvalues and eigenvectors, verify that ax is equal to lambda x. Here is the solution for the first problem for the first eigenvalue, and the solution for the first problem for the second eigenvalue. And here's the solution for the second problem. There is only one eigenvalue. And that's it for this video. Thank you for watching.